Welcome to the Explainer. Today, we're doing something a little bit different. We aren't just looking at data, we're actually stepping into the shoes of database architects. Imagine, you've just been handed this massive, incredibly complex project. You need to take a whirlwind of raw, unstructured concepts and somehow engineer them into a functional, highly efficient data system. Okay, let's dive right into this. Think about your average modern hospital. You've got hundreds of doctors, thousands of patients, endless prescriptions, emergency wards, billing departments. I mean, it is pure chaos if it isn't organized perfectly. A hospital management system is basically the ultimate real-world problem for us to solve today. How do we ensure that the right patient gets the right medication at the exact right time? We have to build a system that literally never fails. So here's our roadmap for the journey today. 1. Blueprinting the ER model. 2. Constraints and database keys. 3. Converting to relational schemas. 4. Mastering relational algebra. And 5. Advanced modeling and EER. Section 1. Blueprinting the ER model. So what is the entity relationship or ER approach? Basically, it's how we translate the messy physical world into a neat conceptual database model. Think of entities as the nouns in our hospital: a patient, a doctor, a room. Attributes are the adjectives that describe them, like a patient's name or a room's maximum capacity. And relationships, well, those are the verbs. A doctor treats a patient. Identifying these core pieces is exactly how we create our structured data representation. But, not all entities are created equal. A hospital patient is what we call a strong entity. They exist in our system no matter what. A specific prescription refill for that patient, however, is a weak entity. It just cannot exist on its own. Think about it. If the patient doesn't exist, the refill certainly doesn't exist. Recognizing these dependencies is absolutely crucial to ensuring our data relationships are accurate. To build this the right way, we really have to put on our engineering hats. We apply a structured approach by first evaluating our problem statements. What exactly does the hospital need this system to do? We identify our core objectives. Then, we analyze and categorize our entity sets and relationship sets based entirely on their functionalities. This careful, structured approach guarantees our conceptual blueprint will actually hold up when we start construction. Section 2. Constraints and database keys. Now we have to establish the physical laws of our hospital's universe, and we do that using integrity constraints and mapping cardinalities. For example, a mapping cardinality rule might dictate that one patient can have many prescriptions, but one specific prescription can only belong to one patient. Applying these constraints and parameters ensures our data stays totally consistent and perfectly mirrors real-world hospital rules. To actually enforce these rules, we use keys. Think of these as the ultimate security badges in our hospital, linking everything together. The primary key is the main identifier, like a unique patient ID, because no two patients can have the same one. A secondary key might be something like a phone number for quick searches. And the foreign key, that's the magical link. It's a badge worn by one entity that connects it directly to the primary key of another, ensuring Jane Doe is perfectly matched to her correct medical record every single time. Section 3. Converting to relational schemas. This is the exact moment where theory turns into reality. Conceptually, our ER model acts as a blueprint. It's all bubbles and diamonds connecting ideas. But our relational schema, that is the actual physical building. It translates those loose concepts into structured, rigid database tables with distinct rows and columns. Getting to that structured reality takes a very precise step-by-step conversion process. First, we take our conceptual ER model designed for our real-time problem. Next, we apply strict conversion rules, like deciding that every strong entity automatically becomes its own table. And finally, we output the completed, structured relational schema. In a fully constructed, real-world hospital management system, this relational model is holding actual data. You'd have a patient ID acting as your primary key to ensure absolute uniqueness, right? Alongside the patient's name. Then you'd have a ward ID acting as a foreign key. That foreign key connects this patient data to a completely separate ward table. This is what the relational model looks like when it's fully built and running. Section 4. Mastering relational algebra. Okay, if the relational schema is the physical building, relational algebra is the language we use to actually navigate and operate it. It's the whole framework of expressions and queries used to extract the exact information we need when a doctor urgently needs to find all patients in ward W04 with a specific blood type. Relational algebra is the underlying logic that makes pulling those exact hospital records possible. We control all this data flow through a few specific operations. Unary operations let us filter data from a single table, like isolating just the patient names. Set theory operations let us combine data, maybe merging patient lists from two different clinics. And binary operations let us seamlessly join multiple tables together. Mastering these relational algebra queries gives you absolute total control over your system's data flow. Section 5. Advanced Modeling and ER. As medicine advances and these hospitals grow, our database absolutely has to evolve right alongside them. To do this, modern teams upgrade from a basic ER model to EER, Extended Entity Relationship Concepts. As our real-time operations become massively intricate, basic entities and relationships just aren't enough to capture all the nuance we need. The ER toolkit gives us some incredibly powerful enhancements. Specialization, for instance, lets us take a generic staff entity and branch it downward. We can specify that they are staff, but more specifically, they are doctors or nurses, and each gets their own unique attributes. Generalization is just the reverse, grouping specific entities into a broader category. And aggregation actually lets us treat a relationship itself as an entity. These advanced techniques allow for just an incredible amount of design nuance. Of course, building something this sophisticated is literally never a solo mission. To implement these massive real-time systems, teamwork is absolutely essential. You have to communicate your database design decisions clearly so every single engineer on your team is on the same page, all while utilizing modern tools to keep your implementation as efficient as possible. So, your hospital schema is built. The relational tables are flawless, your algebra queries are lightning fast, and you've utilized EER for maximum detail. But as we know, technology never stops moving. As new data demands emerge tomorrow, how will you and your team adapt this model? What will the next iteration of your blueprint look like? Keep that architect's mindset alive, keep exploring, and I'll see you in the next explainer.